Okay, so let's take a look at our first example here. So the setup is always going to give you a few things. This one, the linearization, remember that just means tangent line. They'll give us the function, give us the x value. So we're actually going to start with that. Like it says, find the linearization, and then it'll say, and, so that's going to be the second part of our problem. So let's just focus on this part of it first. So find the linearization, that means tangent line. So I want you guys, anytime that you see the phrase tangent line, I want you starting with just this generic setup, and then that way you know all the pieces that you're going to need. You can figure out how to plug everything into the right spot. So this x1, that's your x value. That's always just what's given to you. So that's x equals 0. And then there's two other pieces that you're going to have to find and then plug in. So y1 is what the y value would be when we plug in x equals 0. So like this is, that's given to us. And then the y1, like I said, is what you get when you plug 0 into the function. So that is your f of 0. So we've got square root of just 1 plus 0, which of course square root of 1 is just 1. So that's now your y value. And then for m, the slope at that point, remember we talked about how the tangent line and the curve share the same slope. So all we need to do is figure out the slope of this curve at this point. And then that's the exact same slope that goes right here. So when we're talking about slope, remember that means we mean derivative. So if we want to find f prime of x, so this is like just a mini little chain rule here. Think of this as like 1 plus x raised to the 1/2 power. Okay, so just to write that there, like think of it as 1 plus x raised to the 1/2 power. And then you can do a power rule with that. So power rule says the 1/2 comes out front. You leave this 1 plus x as like a nested function right where it is. The power, we subtract 1, it drops down to negative 1/2. And then technically it is a chain rule. You're going to be multiplying by the derivative of that 1 plus x, but easy for us, the derivative of 1 plus x is just 1. So that ends up being our slope. And then to get this value specifically, we want to know what the slope would be at x equals 0. So we can plug that in. So it's 1/2 and then 1 plus 0 raised to the negative 1/2 power, and I'm not even going to bother writing that 1 because we know it's not going to change a thing. So this we've got 1, even if you raise it to the negative 1/2 power, it still comes out as 1. And then we multiply that by 1/2. So let's get the actual tangent line. So that's the first part. So we've got y minus y1, which we figured out was 1, equals the slope, which we just found is 1/2, and then times x minus the x value. So you find your linearization, you find your tangent line, and then move on to the next part. So then it says use it to approximate the square root of 1.02. So that, if you picture like 1 plus x being underneath that square root, that would be like 1 plus 0.02, kind of like that, which would give you this. So if we have 1 plus x, that means we're trying to figure out what the value would be when x is 0.02. Okay, so what we're going to do is we're going to plug in an x value of 0.02. So that's how we answer the second part of that question. We're going to plug in an x value of 0.02. And then, at the very beginning of the video, we talked about how if you're really, really close to that point of tangency, the tangent line will have almost the exact same value as the actual curve, right? So the tangency point was 0. If we're trying to plug in 0.02, that is very close. That's 2/100ths of a point away. So it should be pretty accurate. So we're going to plug in the 0.02 into our tangent line. So we'll have y minus 1 and then 1/2, and we're just going to literally replace this x with 0.02 and then minus 0. So we'll clean that up, see what it ends up simplifying down to. So we have, on this right-hand side, this will be a weird like decimal inside of a fraction thing for right now. Like we've got 0.02 and then divided by 2, but we can very easily get that cleaned up. So if we divide that by 2, we end up with just 0.01. And then we're going to add the 1 over to the other side. So y is 1.01. So that's our approximations. That's the first part. This is the approximation of what the square root of 1.02 would be. And then every question for this section, I'm going to ask you, is this value an overestimate or an underestimate, or an over approximation or an under approximation? The way that we are going to answer that question is by using the concavity of our original curve. Because if you remember talking about this in class, one of two things will happen. Let's say that our graph is concave up, something like this. Any tangent line that you have besides the point of tangency would go slightly under that graph. So that would be an under approximation, just a little bit lower than what the actual value would be. And then by contrast, if you had something that was concave down, any tangent line that you graphed, again, except for the point of tangency, would be just a little bit above the graph. So to answer whether it's an over or an under approximation, you would have to figure out whether the original function was concave up or concave down at that point. And the way that we do that, as we figured out earlier in the chapter, is by looking at the second derivative, because the sign of the second derivative will tell you the concavity. So we are going to take a look at f double prime. Look at the second derivative. So here's our first derivative right here. So another little power rule, this negative 1/2 is going to come out front. That'll be negative 1/4. The 1 plus x is going to stay in place. And then my power drops down to a negative 3/2. And then, of course, times another 1 because you technically have this chain rule, but we know it's not going to change our function. So this right here, this negative 1 plus, or negative 1/4, of course, is a negative value. This piece right here, if we like rearrange a little bit, we'll have negative 1. And then my denominator will be 4. And then this whole piece right here, this is like the square root of 1 plus x cubed. That's what that power means. So if you're looking at this, we're trying to figure out if it's positive or negative. If I plug in 0, or if I plug in 0.02, 1 is positive, I cube it, it's positive, I square root it, it's positive. So this whole denominator is going to be positive if I'm plugging in something close to 0. And then the numerator is negative. So we know that second derivative is going to come out to be negative, just like at those values that I'm looking at. Not always negative, but right around that range. So it's going to come out to be negative, which means our graph is concave down. And if our graph is concave down, that makes this an over approximation. Okay, so I know it sounds like a whole ton of work just when we're looking at this very first one, but that concept will start to make sense to you, the whole over or under approximation idea. Okay, so next let's take a look at example 2. For both of these examples, we're doing the exact same thing. You're going to come up with a tangent line. You're going to use it to approximate a different value. So the linearization of cosine at pi over 2. So remember, we're going to start just by writing down our generic tangent line so we know where everything plugs in. So first we've got the actual x value would be pi over 2. The next thing we want to know is what the y value is at pi over 2. So that means we're going to take that and plug it into our cosine function. So this is why I always stress the importance of knowing the unit circle. You never know when an example like this is going to pop up. So cosine of pi over 2, picture that's the very tip top of your unit circle, and the cosine is the x value. So that would actually be 0. So this we've got just y minus 0 would be our y value. And then for the slope, we need to know what the derivative is. So our generic derivative, the derivative of cosine, remember just from our basic derivative rules, is negative sine. So then if we wanted to know the actual slope at the point of tangency, we plug in the pi over 2. So we'd have negative sine of pi over 2. So sine of pi over 2, again, tip top of the unit circle. The y value would be 1. But then, of course, we've got a negative sign, so this would be negative 1. Okay, so that is your slope. So that is our linearization, aka our tangent line. So we always start with that, like find the linearization. Okay, so we got it. Then it says use it to approximate the cosine of 1.75. So we can plug in that 1.75 and see what you're going to end up with. So if we do that, we would have y, and I don't have to write the minus 0. And then negative 1, so I plug in 1.75 minus pi over 2. So as really ugly as this looks, it specifically says without using a calculator. So if I don't have a calculator on me, I would have no idea what this weird irrational number would come out to be. So we're actually going to leave it. This is considered to be an exact value, which I know is a little bit strange. One thing that we could do if we really wanted to simplify, like if this was driving you crazy that it looked like this, so let's say we keep the negative on the outside. So 1.75 is 1 3/4, which would be 7/4, and then minus pi over 2. So like we could get a common denominator and combine these up. Like we could do 7/4 minus 2 pi over 4. So like if we really wanted to actually clean these up, we could write this, so distribute the negative. We'd have 2 pi minus 7 all over 4. So I guess you could do that. That's about as far as that would go. But again, without a calculator, you're not going to have a decimal.
If you're still in the building, please come to the main office. Levy Reynolds, if you're still in the building, come to the main office. Thank you.
sorry. I'm in my classroom, obviously. So then we can answer that last part. Is this value an over or under approximation? So just like example 1, just like any example, we're going to figure out the concavity of this graph at this particular point. So this one's important because a cosine curve, if you're picturing it, it just kind of wiggles up and down, back and forth, which means it's constantly changing concavity. It's important to know what the concavity is at the point of tangency, because the concavity will be changing, so we need to know what it is at that point. So to find the concavity, we're going to find the second derivative. So second derivative would be the derivative of the first derivative. So the derivative of negative sine would be negative cosine. So we want to know what the second derivative would be at the point of tangency. So negative cosine of pi over 2. So we plug that in and we come up with -0. So that part gets a little bit tricky. It's like, okay, if we're getting 0, that's neither concave up or concave down. That's actually a point where you would have no concavity at all. So the next thing we would need to know is what the concavity would be at 1.75. All right, so let's get our concavity at 1.75 instead. So now we have negative cosine of 1.75. And pi over 2, if we picture what like 3.14 would be, pi over 2 is about 1.57. So this is just a little bit past pi over 2, a little bit larger than pi over 2. So if we visualize what that would be, you're going a little bit farther on the unit circle. So just to give you a little visual. So like here's pi over 2. 1.75 would be just like going a little bit farther in that direction. And as soon as you pass this point over here, cosine becomes negative. So like over here in this second quadrant, cosine's negative, but then this is negative cosine of 1.75. So we know this is going to be a negative value, but then we're making it negative. So this is going to come out to be positive. So our second derivative is positive, which means our graph is concave up. And if our graph is concave up, that means that your approximation would be underneath the tangent line. So this would be an under approximation. Okay, and then last example here. So I give you guys some slightly different directions for this one, just so you could get used to it either way. So this one, we are kind of creating our own equation. We're gonna go off of that. So this one, you figure out what your f of x would be. So your function would be just the square root of x, and then we're gonna have to have a point of tangency. So the square root of 123 is not something that comes out evenly. So basically your task is to figure out what's the closest thing to that does come out evenly. And that would be the square root of 121. So our point of tangency would be 121, okay? Because the square root of 121 is 11, so it's a nice, neat value. So linearization, start with our little formula here. We know the point of tangency that we're talking about is 121. So if we do our little side work here, when we plug 121 into the original function, we know that the square root of 121 is 11. So that's going to be your y value that goes right here. And then you need to know the slope at that point as well. All right, so we want first just the actual derivative function. So the derivative function, remember this is like x to the 1/2. So the 1/2 comes out front, and then the power drops down to -1/2. No chain rule, nothing fancy here. So then if I plug in 121, I have 1/2 times 121 to the -1/2 power. So 1/2, and then 121 is the -1/2, remember means the reciprocal of the square root of 121. So that would be 1/11. So that is 1/22 would be our slope at that point. So we can throw that right into the tangent line. It's 1/22. So we know that now. So once we know that, we can plug in 123 and then get that approximation. Okay, so to get the actual approximation that we're looking for, we plug in 123 for x, which is relatively close to the point of tangency. We've seen some that are a lot closer. So this will have 1/22. And then when I subtract this, I get 2. So of course this simplifies out to be 1/11. So when I add that 11 to the other side, I get 11 and 1/11 would be my approximation. So that's the first part, is actually finding the approximation. And then of course, just like the other two, I'm gonna ask, is this value an over or under approximation? You find the second derivative, check the concavity, and then you can answer that question. So second derivative, f double prime, the derivative of the first derivative. So the negative 1/2 comes out front, gives us negative 1/4, and then my power drops down to negative 3/2. So if I plug my point of tangency in, I would get negative 1 over and then 4. So now I'm going to plug that 121 in right here. So 121, and then this would be listed as 3/2. It's not negative anymore because I flipped it down into the denominator. So I don't really have to figure out what this is. I just know that 121 raised to 3/2 power is positive, times 4 would still be positive, and then if I have a negative divided by a positive, I know that's going to come out to be negative. So if my second derivative is negative, that means my graph is concave down, which means the tangent line would go over. So the value that I just created was actually an over approximation. And the farther away that you get from the point of tangency, the worse that approximation is going to be. So if I had wanted to know the square root of like 121.1, it'd be over, but it wouldn't be that much over because it's really, really close to the point of tangency. I'm a full 2 units away from the point of tangency, so it's going to be an over approximation. It's actually probably going to be fairly far away from what the real value should be, because as I move farther away from the point of tangency, I kind of lose some of the accuracy that I would have. All right, so that is how you do linearization and their approximations.